So last week we looked at an example from the book about eating organic and chemicals like pesticides. The book had an example of, I think it was called 3-PBA as a pesticide that can be a problem that is commonly found in non-organic foods. And so what they were looking at here was, is there a difference before eating organic versus after in a person's body? And the book gave some data about that. I'm just going to rough it out on a graph here. And they went for a 99% confidence interval. I'm going to go for a 95 just to review that 95% rule for my confidence level. So in their data, they found, don't state the mean. I have to guess at that in a moment, but they do state the boundaries. So they said 17.5 was the estimate there, and 30.9 was the estimate here. And we're looking at average difference in pesticide here. So again, we're looking at a difference. So they found the average amount before eating organics and they found the average after eating organics. Oops. Trying to define my variables so I know what we're talking about. And they created, based on those two, a new third variable, the average, the difference of the averages, which was the average before minus the average after eating organics. So the belief was, and the data showed, that people had more of this chemical when they weren't eating organic food than they ate organic for a couple of weeks, and they had less later. So we should expect this to be a positive number greater than 0, because we're measuring how much they had there. And how did they measure those? That was micrograms. So a couple reminders about confidence intervals here. Here they gave me the lower and the upper bound, but they didn't give me the mean, the point estimate, and they didn't give me the margin of error. So I want to calculate those two. So the mean difference is just going to be the average of those two to put me in the middle. So what is 30.9 plus 17.5 divided by 2? And then I also want to find their margin of error here. And that would be to subtract the upper and the lower and then divide by 2 again. So 30.9 minus 17.5 over 2. Calculator, and parentheses to do the difference first. 30.9 minus 17.5 divide by 2. That's going to give me the margin, 6.7. And then switch to a plus to get the middle. 24.2 should be in the middle of the distribution. And then this was our margin over here. Switch colors, come on. There. And we have a 95% confidence interval. believe that the average difference before versus after of the amount of 3 BPA in someone's system is somewhere between 17.5 micrograms and 30.9 micrograms. And back to my, so that's just the confidence interval, right? What's the average difference? The average difference about 24.2 micrograms, plus or minus 6.7%, right? So that's the estimate of the population parameter. So there's a couple of interesting things about this. First is the confidence interval. And the confidence interval just says, hey, we think this population number is in this range. Interval. Yeah. So we are 95% confident that the difference in the mean PBA, 3 PBA, before eating organics to after is between 17.5 micrograms and 30.9 micrograms. Yep. All right, so that's just our estimate, somewhere in there. Often we'll just state the mean. So if we were to look this up and this was in a news article, they would probably say, we just think it's about, the difference is about 24.2. And then there'd be a link to look up the original report, and then they would talk about the margin of error. So alternatively, instead of saying between here, they might just say is 24.2 micrograms. And then thered be some fine print that says plus or minus 6.7 micrograms, right? Margin of error. So there's a couple of ways we report that. Now, the other thing, the more interesting question, is this difference significant? And that's a trickier question to answer. And the way I tried to answer that last week is just to say the following. Well, is it possible that there's no difference? Well, anything's possible, but is it likely here? So if I think about the idea of no difference, that would mean that mean difference that we calculated, is it possible it's equal to 0? And if I look back at the confidence interval, is 0 in that interval? So we go back here, we look at the interval, here's 17, here's 30, 0 is going to be somewhere over here-ish. So here would be x bar equals 0. Is 0 anywhere near the interval that we think the range is in? And the answer is no, it's not. So based on this sample, there is very little chance there's no difference. That eating organics doesn't matter for the amount of pesticides in somebody's body. And the application for last week was a similar example to this, where we looked at, okay, there's this difference in these two quantities. Let's find a range for that difference. What does it look like? Tell me what the confidence intervals. That was most of the problem. And then there was just extra question at the end. Well, could it be there really is no difference? Like with the exercise hours for men and women, the data showed a difference, but it really wasn't significant because 0 was in the confidence interval. In this case, 0 is not in the confidence interval. So it looks like it's pretty unlikely. Now, here's the problem though. What does very little chance mean? Very little chance, well, that's probability. So the probability is low. So the next thing we have to learn to do in statistics is we can make these confidence intervals. We're getting better at doing that to estimate something about a population. But then if we want to ask important questions about that, to question those estimates that we have, now we have to start getting into probability. So the question here is, what does it mean to have a small probability of happening? And emphasis here is that means we have to figure out what does small mean? And it turns out it depends. And this idea of measuring what a small probability is related to a question about data, this is the idea of a hypothesis test. So hypothesis tests help us answer this. Hypothesis tests attempt to answer questions like this. And so again, the question I was asking back here, is there a difference before versus after of eating organic foods? And the confidence interval seems to indicate that, that there is a difference, and it's pretty unlikely that there's no difference. But I don't know how to measure what unlikely means yet. I want to put a number to that. Like, I got my COVID vaccine, and a friend of mine is putting his off because he heard a lot of people got sick after their second shot. What does it mean to get sick after the second shot? Well, their body reacted to it, which is what we want to have happen. And then maybe a doctor might say, you know, there's a 5% chance that you'll be sick in bed for a day or two. And I'm just totally making that up. I don't know if that's true. 5% chance of feeling ill after second vaccine. And okay, so there's a 5% chance that if I get it today, tomorrow, I'm gonna probably spend the day in bed. Oh, that's not too bad. I think I'll go for it. Now, what if they said, hey, there's a 5% chance that you're gonna die from this? Then, you know, being sick in bed is one thing, right? Dead is totally another. 5% chance I'm gonna die, hell no, I'm not getting that. Right, so there's a difference in saying there's a 5% chance that you'll feel a little ill versus there's a 5% chance that you're gonna die. I want way smaller than 5% chance for death. For death, I want it to be like 0.001% chance of death. That's more satisfactory to me. I want it to be way more likely I could die in a traffic accident near my house than I would die of getting some, you know, something that's supposed to help me. Yeah, and question, it depends on which vaccine you get. Yeah, so it depends on so many things, right? Which vaccine you get, your body, your gender, your, you know, life experiences. But we're trying to generalize for a whole population here. And again, I just made up the 5%. I don't actually, there is data out there for it. I just can't grab it in a few seconds right now. But the point I'm getting at here is, what does a small probability mean? And sometimes 5% is small enough. Okay, that's worth the risk to me. But sometimes 5% is too big, right? So we have to decide what is a significantly small percentage of something happen. And again, sometimes it's 5%, sometimes it's 0.001%, depends on the situation. The general rule is 5% chance of happening for non-life-threatening things. So 5% chance for non-life or death stuff. And that 5% right there kind of comes from the 95% rule. 95% is the usual things. And outside of that 5%, that's the unusual stuff. And sometimes when we're talking about that 95%, so far, we put the 95% in the middle, which means the 5% had to be split into the tail. So it could be 2.5% on either side. But there are going to be cases that we're going to come across today and tomorrow and in the future where we're more concerned about the upper or lower end. So that the line that we draw might be over here, and the 95% is everything below that point, and we put 5% in the upper tail. Or it could go the other way. So we're going to use that 5% in different ways. Could go the other way. It could be the usual stuff we want to happen is up here on the right side, and then we're going to put that unusual stuff over here. Okay, so remember the 95%, this is what we expect to happen, the usual cases, normal stuff. Usual. Middle, usual. And then that 5% is going to be the unusual stuff, the stuff at the extreme ends. And sometimes we're only worried about unusually high things. Sometimes we're worried about only unusually low things. But other times we're worried about unusually low or unusually high. That's a concern. So here we have two unusual regions. So we're moving from confidence intervals where we estimate a population parameter to then asking questions about that population parameter with something else and saying, okay, is this thing unusual? So let's look at a simpler example of this, which is human body temperature. So my daughter has had some bad luck with illnesses. She had COVID in the beginning of last month, and then she got strep throat last week and had to go to the hospital. And so we were taking her temperature all the time. And we all have this idea about what's normal for body temperature and what's abnormal for body temperature. So human body temperature. And we think that mu is population. We think it's about 98.6 degrees Fahrenheit is the commonly quoted body temperature. So this would be population mean. Now, I want to take some data that the authors of our book collected from students, college students, and look at their body temperature and make a confidence interval and see how it compares to what we expect. So this is over in StatKey. Tab, please. There we go. So I'll put this in the chat and in the YouTube description. And I want to do a confidence interval. So I'm in this middle section here, and I have a mean, not a proportion, not a difference. So this top one. And they already have, I believe, data here, human body temperature here. Okay, so this is the body temperature of 50 randomly selected college students from a bigger sample they had of data. They have a dot plot here, which is like a histogram. And so we can see most people are between around 97 and 99-ish. And then we have somebody out here, 100, almost 101 degrees. Maybe that person shouldn't have been in class that day, or maybe they just run unusually hot. So what we want to do is to get an estimate of what the sample tells us about the population, we have to repeat this sample over and over again. And so that's this generate thousands of samples here. So based on this original sample, we're going to say, okay, if this is what a usual group of 50 people looks like, let's resample from that a whole bunch of times to see what kind of variation we get. And we can see every time we do that, down here on the right, if I look at these different points, I can see there's always going to be variation in other samples. So if this is usual and we resample from it, what are the possible things that can happen? So here the mean was 98.26. Resampling, we see we can get a mean as low as an average for 50 people. Now, none of these are individuals. So this one right here is 97.93, average of 50 people. This one over here is 98.62. And so let's just generate more. Get more of a bell-shaped curve going on. Okay, that's looking pretty good. I'm at 7,000. And let's go for the usual 95%. So according to this sample, average human body temperature, we're estimating to be somewhere between 98.059 and 98.478. So let me draw a picture of that. So this was our population. Now we have a sample. And in our sample, we had n equals 50 people, not a very large sample there. And yeah, so, okay, from healthy adults. So that, yeah, 100 is interesting. So we'll talk about how that relates. And let's see, the mean was 98.26. And when I run the sampling distribution, we have three things going at once here. We have what we think about the population, we have information about a sample, and then we're using that sample to generate a sampling distribution, which is a totally different graph and numbers, sampling distribution. The sampling distribution is thousands of samples, all at size 50. What do their means look like? Distribution. And that helps us estimate what's happening with the population. The sampling distribution had a mean, and that's usually called mu x bar, which the book mentioned, but I haven't written that down in class before, 98.262 on my version of it. And they also gave me a standard error on that, which is the standard deviation of this sampling distribution of 0.107. And then the graph of that would look like this. We're putting 95% of samples of size 50 in the middle. That puts a temperature, an average temperature, let's call that X bar for now, of 98.262. And out on the left, they thought the lower end for the population should be 98.059. And the upper end, Stackey says, is 98.474. And so the margin of error is that our estimate of the distance from the center of the edge, we get that by taking the upper minus the lower, cutting it in half. So I'm going to put that on the calculator. $98.478 minus 98.059. And if all of you went to Stackey and ran another simulation, you won't get the exact same numbers, but they should be pretty close to mine. Once in a while, something weird happens. I think I typed those right. 98.478 minus 98.059. So I'm getting a standard, a margin of error of about 0.2095. Now, using the 95% rule, remember, I'm going to keep bringing this up a lot.
I'm confused. On your calculation, you used a 99 something, but on the chart here, you have 98.474.
Back here, did I miscopy something? So here's my simulation and stat key. I'm aiming for 95% in the middle. So my lower end is 98.059 and my upper is 98.478.
Right. So when you did your, yeah, when you did your margin of error, you said 99 something.
Oh shit. Thank you. 90, no, I got 98 here, 98.4. Maybe I misspoke, but I don't think I mistyped. 98.478,
oh, okay.
98.059. Yeah, sorry if I misspoke. I think I got them typed correctly. And I was just going to go over how to double check, because every once in a while I misspeak or mistype, and I'm sure you guys have a similar problem. And so what I was going to do to check that I got the right margin of error here is compare it to the standard error. And if I'm using the 95% rule, the 95% rule means that's 2 standard deviations on each side. So that from the middle to here should be about 2 standard deviations, which is the standard error on this graph. And the standard error is 0.107. So if I were to double that, that should be about the margin of error. So for 95% confidence interval, the margin of error will usually be twice the standard error. So if I double that, I get what, 0.214 versus 0.2059. If we rounded both of those to 2 decimal places, that would be about 0.21, and this one would be about 0.21. Right, so they're close to each other. So what does this tell us again? So based on this sample of healthy adults, we think average human body temperature is somewhere between 98.059 and 98.047. And the interesting thing is 98.6 is not in the interval. So 98.6 is somewhere out here. It's not in my interval. So a couple things. One, maybe this is just a weird sample of healthy adults. 2, maybe 98.6 isn't true. And it's could be a little bit of both. There's more evidence that average human body temperature has been dropping. So it's less than 98.6, and that's what this seems to indicate here. We've been doing estimates of means and proportions. Now, the population also has a standard deviation, which is based on studies, is believed to be about 0.7, right? So that's the standard deviation of the population. So population STD is believed to be about 0.7 degrees Fahrenheit. The standard deviation for the sampling distribution, notice that's much, much smaller. That's 0.1 degree Fahrenheit roughly. So remember, there's a difference between a population, a sample, and a sampling distribution. They're related, but they're all different. With this 0.07 idea here for the population, we expect most people to be within 2 standard deviations of the mean. So if I think about like checking my daughter to see if she has what we call a fever, what constitutes an unusually high temperature, we usually consider that to be about 2 standard deviations above the mean. So if I double 0.07, that gives me 1.4. If I add that to 98.6, that means I would expect the average healthy adult to have a body temperature up to about 100 degrees, and that's okay. Somebody could be lower than that though. Like I run around 97.5 whenever I take my temperature and I'm feeling okay. So I tend to be much cooler than say my wife or my daughters. So there's lots of variation in everybody's body temperature. Your body temperature varies throughout the day. And then it also varies based on what's going on in your life in terms of fighting off some kind of illnesses that's going on in your environment. So back to this right here. So again, 98.6 is not in this interval. It's outside. If there's 95% in the middle, that gives the tail 2.5% on the right. If you look back at my stack key graph here, it's got a better number line than I have. We can see 98.6 is way out here. So if this whole red area is 2.5% of all possible samples, then I'm guessing that this part right here is probably 2%. So this is on the edge of the upper 0.5% of possible samples that we might get, which is pretty rare, right? So I'm guessing there's like 0.5% chance, if this is a good sample representative of the population, that we'll find a sample where the average of 50 people is 98.6%. So I'm kind of estimating the percent of that happening based on the sampling distribution. What we're going to switch to instead here is doing this with what's called a hypothesis test. And I want to try to explain the difference. So that was a confidence interval. This week's topic, again, hypothesis test. Hypothesis test. So hypothesis test is based on a question and typically some belief, or maybe it's a fact based on data. So my question here is human body temperature less than 98.6? Degrees Fahrenheit. So that's my question here. Now, when you make a hypothesis test, you have to reference a parameter and a population. So my population here is all humans. Population humans. And the parameter of that population, the thing I'm trying to measure, trying to estimate, parameter, that would be the average body temperature. And it's an average, so it gets the symbol mu. So mu is the symbol for my population parameter. It's average human body temperature. And the belief is that it is 98.6, and that is what we call a null hypothesis. And what we're going to try and do today is distinguish between how do we identify what the null hypothesis is. So null hypothesis. So my null hypothesis would be that mu equals 98.6. Now, the question that's asked, sometimes it is the null hypothesis, but sometimes it's what we call an alternative hypothesis. So I have this alternative to that. Alternative theory, hypothesis. And my alternative is that I think it's actually less than 98.6. Some important things about identifying based on the question asked, which is which, is a null hypothesis has a 0 in it. Sorry, has an equals in it. Has equals. And the alternative hypothesis cannot have an equals. So as soon as up here I ask my question with the less than there, immediately that has to be the alternative because it doesn't have an equals in it. The options for a possible null hypothesis, the null hypothesis could have an equals, it could have a less than or equal to, or it could have a greater than or equal to. Null hypothesis is going to be one of those three things. The alternative hypothesis could be a not equal. Otherwise, it's going to be a less than or a greater than. So types of symbols that can be in the null hypothesis are an equal, a less than or equal to, or a greater than or equal to. So if somebody asked a question that led to a less than or equal to, then that would have to be the null hypothesis instead of the alternative. So the question asked isn't necessarily the alternative. It depends on whether there is an equal sign in it. And there's three symbols that we play with that have an equal sign. They are the straight equal symbol, the less than or equal to, right? There's an equal there too, the greater than or equal to. So we have to evaluate each situation. Is equal present or not? If it is present, that has to be the null hypothesis. If it isn't present, that's the alternative. And then picking the other one, there are options. So my question was the alternative hypothesis, right? It's a less than. So the question is my alternative. To pick the null hypothesis, I have two options. I could just go with equals because that's what I was told all my life, but I could go with the opposite of less than, which being greater than or equal to. So there are some people would have said instead of equal to, they might have said mu is greater than or equal to 98.6 as their null hypothesis. And that's okay too. Again, I chose to do the equal to just because that is the common knowledge that's given out. It's not body temperature is at least 98.6. It's average body temperature is 98.6, right? So I'm not going to choose that one right there. So the way these hypotheses work is some kind of question is being asked. If the question has an equal to in it somehow, then that is the null hypothesis. If it doesn't have an equal, it's the alternative, and then you got to figure out what the other one ought to be. Sometimes that's straightforward, and sometimes it's just you have to make a choice. All right, so next. So I have my question. I turn my question into hypothesis. Sometimes those are abbreviated with less words because unfortunately math people like to write as few words as possible. In this class, we bounce back and forth. So often the null hypothesis is going to be written as an H with a subscript 0. Null means nothing or 0. And so that's why we put a 0 there. So often we'll see this abbreviation for the null hypothesis, H subscript 0, and then a colon, and then the equation. So mu equals 98.6. And then the alternative is either written as H with an A for alternative, and then whatever its equation or inequality is. So in this case, mu is less than 98.6. But sometimes people, instead of the HA, they might write H1, like 0 versus 1. This is my default hypothesis. This is my number one new hypothesis there. So you might see that sometimes. H1 is less than 98.6. Okay, so to make a hypothesis test, again, we have to have some knowledge about the population or some belief about the population, and we have to have a question, and we put these together in the two different hypotheses. And then we need a sample. So then we have to get a sample data to test the hypothesis. And again, reminder, we are testing H0, the null hypothesis. Human body temperature is 98.6 versus our alternative hypothesis, mu is less than 98.6. And I get some sample data. And to do this with StatKey, we actually need the whole data set. So for StatKey to run this test for us, we need the original data. It's not enough to just be told what the mean is. So if somebody came up to me and said, oh, I want to test this hypothesis, my sample mean was 98.26. Right, so I know that for sure, X bar for this sample is 98.26. That's not enough information for me to run a hypothesis test in StatKey. I need all of the data that led to that mean. Tab, I'm pretty sure the same data is also located in the hypothesis test for a mean here. So I'm switching. So if you were on the StatKey page too, you could just hit the StatKey logo here. That'll take you to the home page, and then we're going to switch to test for single mean, and this is the same data. Mean is 98.26, standard deviation is 0.765. Yep, same data set. So if you want the direct link, here it is. Now, the difference between a hypothesis test and a confidence interval is with a confidence interval, everything's centered on the data. In a hypothesis test, everything is centered on the population. So we're running a hypothesis test, and that's going to be centered on the population null hypothesis. So I'm going to start drawing my rough sketch of what's happening here by drawing my best bell-shaped curve. And unlike a confidence interval, where we put the 98.26 in the middle, with a hypothesis, we put the population value. So we're going to put 98.6 in the middle. And then we have to figure out, okay, so if we run a whole bunch of other samples like this 50, what kind of variation are we going to get around 98.6 if that's what's expected to happen? So prior knowledge is we expect sample means to be about 98.6, right? Because we're told over and over again, what's human body temperature? That's about 98.6. So when you're in StatKey, two things you gotta make sure are set correctly before you start. Number one, do you have the right data? So either switch to the right data or edit and drop your data in there. Once your data is in there, you need to next check, do you have the right population center? And so here they gave me 98.6, otherwise I would have to go there and type it in. So I have my data, I have my null hypothesis set, and then I generate. And usually I like to get at least 6,000, so there's 6,000 right there. So then I ask the question, all right, if we're expecting 98.6 to be the mean of all samples of humans, how weird is this 98.26 for my sample? Now, because I chose this less than right here, a less than puts me, on this side. So I'm somewhere over here, right? This is less than. Would you agree that less than means that I'm on the left side? Right? So that means because of the less than, I'm running what's called a left tail test. So whereas before, when we did confidence intervals, we always selected two tail. Here, I have to look at my alternative and say, oh, is it a left tail, two tail, or right tail? In this case, it's a left tail because my alternative was a less than. So I select left tail, and then I just type in my sample data down here. My sample mean is 98.26. All right. So StatKey says if you expected the population average to be 98.6, and you have a sample of 50 people with a mean of 98.26, this is their estimate of the probability of that happening. So StatKey says it's about 0.0005 is the probability. So I'm going to write down what that means. I'm going to just add this to my graph. So we put X bar goes here. That's the 98.26. And 98.26 is definitely less than 98.6, right? I'm on the left side, correct. And then StatKey calculated that the chance of getting other samples in here, I'm going to call that a probability, was 0.0030. Double check. 1, 2, yeah, 3 zeros. 0.005 is the probability. Now that's just a decimal. If you wanted to change that to a percent, you would multiply by 100. That moves the decimal twice. So we could also say this is 0.05%. percent, right? It's 1/100% chance that we're going to get a sample of 50 people that have an average body temperature of 98.26 if we were expecting the temperature to be 98.6. This is one of those conditional probabilities that we were looking at back in the probability chapter. So if I write probability, I'll do this in probability notation, and then I'll put it in English to the best of my ability. So we just calculated in StatKey the probability of finding a sample mean that is smaller than 98.26 when we were expecting, and so usually I put a vertical bar in the textbook, they often put an if here, if we were expecting the mean to be 98.6. And we find that probability to be wicked small. So this is wicked unlikely. Sorry, I should say extremely. Extremely unlikely. So one of two things, like that shouldn't happen. That's like hitting the lottery almost. So one of two things is wrong. Either this is incorrect, I shouldn't have made that assumption, or I've just got a really unusual sample. Okay, the claim here is that there is a good sample. So claim to have a good sample. So if the sample isn't the problem, then that mu equals 98.6 is the problem. It's questionable. So what I have here is evidence that human body temperature is not 98.6. Sample evidence. Mu is not 98.6. Now, my data is to the left, and that was my alternative hypothesis. So this data supports the alternative. This sample is evidence that mu is actually less than 98.6. Now, it doesn't mean that average human body temperature is 98.26. That's just this particular sample, and samples will vary. Our confidence interval tells us that we think, based on the sample, actual body temperature has an average of somewhere between 98.059 and 98.474. So a lot of times we'll use confidence intervals and a hypothesis test together. Sometimes we'll start with a confidence interval and then go to a hypothesis test to get some kind of probability of this happening. Other times we start with a test and say, whoa, look at this. We better do a confidence interval to see what the actual range might be. So they almost always go hand in hand. But the idea is we have a question, we have some data, and we try to use the data to answer that question and give a probability to this kind of thing happening. Sometimes the probability is going to be small, like, whoa, that shouldn't happen. Why did that happen? Other times the probability is going to be big and say, oh, okay, nothing new here. So we're just going to look at a couple more examples of this. Quick summary of this idea of how to run the test.